Hello everyone, this video is on field and integral domain. In the hierarchy of algebraic structure, field it comes after division ring. So field it is a division ring that is commutative, and the integral domain it comes after commutative ring and ring with unity. An integral domain is a commutative ring with unity that has no divisors of 0. So a field it has multiplicative identity, it has multiplicative inverses of each element, and the operation of multiplication is commutative in field. Whereas in integral domain, it has multiplicative identity, it is commutative under multiplication, and it has no divisors of 0. Now the ring of real numbers. It has 1 as multiplicative identity. All real numbers they have multiplicative inverses, and the multiplication is commutative in real numbers. So the ring of real numbers is a field. Whereas the ring of integer is an integral domain. In fact, the name integral domain is derived from the name integer. In the ring of integer, there is 1 as multiplicative identity and the multiplication is commutative. For any two integer xy such that xy equals to 0, we have either x equals to 0 or y equals to 0 in integer. So the ring of integer has no 0 divisors and is an integral domain. Now let me make the concept of integral domain more clearer with an example of ring that is not integral domain. Consider the ring Z6. In ring Z6, the operation of addition is addition modulo 6 and the operation of multiplication is multiplication modulo 6. We have 2 into 3 equals to 6, so 2 multiplication modulo 6 times 3 equals to 0 because the remainder of 6 when divided by 6 is 0. This shows 2 is not 0, 3 is not 0, but 2 multiplication modulo 3 is 0, and this shows 2 and 3 are the divisors of 0 in Z6, so Z6 have divisors of 0 and Z6 is not an integral domain. Next we study two theorems that makes link between field and integral domain. First theorem states every field F is an integral domain. Suppose A and B belongs to F such that product of AB equals to 0. Then B not equals to 0 implies the multiplicative inverse of B exists in F because F is a field. Now operate on both sides on right by inverse of B. This gives us A equals to 0. Similarly, we can show that A not equals to 0 implies B equals to 0. Then we have AB equals to 0 implies either A equals to 0 or B equals to 0. This shows F has no divisors of 0, so F is an integral domain. Before we prove second theorem, we have a lemma to discuss. The lemma states the cancellation law holds in R if and only if R has no divisors of 0. First we prove the cancellation law holds in R. For that, consider A, B and C be any elements of R such that AB equals to AC. To prove cancellation law, we must have A not equals to 0. Then we have AB minus AC equals to 0. That implies A times B minus C equals to 0. Now A not equals to 0 implies B minus C equals to 0 because R has no divisors of 0. This gives us B equals to C, and this proves the cancellation law holds in R. Next we prove R has no divisors of 0. For that, consider the product AB equals to 0. A not equals to 0 implies AB equals to A dot 0. Then from cancellation law we have A cancels out, B equals to 0. Likewise, if B not equals to 0, we can show that A equals to 0. This shows R has no divisors of 0 if R holds cancellation law. This proves the lemma. Second theorem we have is every finite integral domain is a field. Now the only thing lacking in integral domain from field is the multiplicative inverses of each non-zero elements. So to prove this theorem, we'll find the multiplicative inverses of each non-zero element of this finite integral domain. First we have let 0, 1, a1, dot, an are the elements of finite integral domain I. Second, suppose A not equals to 0 is an element of I and we multiply each of these elements by A to get these elements A0, A1, A1, dot, AAN. Third, if possible, let any two of these elements are equal. Say AAI equals to AAJ. In that case, AI equals to AJ from left cancellation law since I is an integral domain. This shows AAI equals to AJ, so all these elements in these products are distinct. They are all distinct. Now since all of these elements are distinct and they lie in I, but the elements of I are these elements, so these two sets, they must be equal. So at least one of these elements must be equals to 1. A0 equals to 1 is impossible because A0 equals to 0. So either A1 equals to 1 or AI equals to 1. If A1 equals to 1 implies A equals to 1. And AI equals to 1 implies AI is the multiplicative inverse of A not equals to 0. This shows every non-zero element of I, a finite integral domain, has a multiplicative inverse. So I, a finite integral domain, is a field and the theorem is proved.